Excellent. Here we go. Thank you.
Ah, okay. Thank you, Dr. George.
You're welcome.
I'm afraid my talk is on a much narrower topic than the others in here. I'm looking at a particular technique in applied mathematics, which historically has been hard to motivate, and due to a new development, multiple timescales that has become fashionable in the last, well, really 50 years, it opens up the possibility of teaching this in a broad manner. If you remember your differential equations, you will have no trouble following the talk. Otherwise, I'm afraid they may be painful. I'm going to look at these procedures for approximating solutions to differential equations that you can't solve by the classical undergraduate techniques. The power series, very well known, she's in all the books. Perturbation series, which is sort of a different way of looking at power series. And then it has a problem which was uncovered and studied by Poincare and Linstedt, and they proposed a different kind of procedure for solving it. But the procedure is very difficult to motivate, and with the new technique of multiple timescales and approach I'm trying to promote here with this talk, it will ease up a little bit. We'll be focusing on trying to model two classical problems here. This is a resistor in parallel in series with a capacitor. It models a diode, but the resistor, instead of being given by the usual Ohm's law rule, has a nonlinearity in it, which helps make the thing more realistic, but it makes the solutions much harder to find. And this is the classic mass spring oscillator, but the spring constant here is not really constant. As the spring stretches, the stiffness becomes higher. And so this is the Duffing nonlinear spring model. And we'll be looking at these. The point here is we have all these powerful tools for solving these problems numerically. But if you're an engineer, it is not an academic exercise to solve it. You need to know from your solutions how the nonlinearity affects it. And it's hard to read this off from reams of pages of data and graphs. It's better if you have even an approximate solution, but with a closed form that you can look at and see what it is you're focusing on and see what its effect is. So the goal here is to find approximate analytic formulas for these solutions. Now, the classic technique for approximating virtually anything is with the power series, which expresses the solution as polynomials. That's very nice. And they have nice properties. They converge. They have analytic properties. But the trouble is, polynomials will behave very nicely in a small region. But as you get away from that time, as time evolves, they've got to be polynomials, which means they're going to go crazy. They're wild, and they you have trouble tracking your solutions. Here we see the polynomial. I mean, the classic engineering functions that you need to be able to model are exponentials and sinusoids. And here you see the polynomial approximation for a single sine wave takes 9 terms. And no one wants to compute 9 terms for this. And you can see that the polynomials just go crazy after a while and can't follow this. If you're trying to follow a lot of periods of a high frequency wave, this would be useless. And the same thing occurs also when you try to follow a decaying exponential. If you take a 7-term polynomial approximation to a decaying exponential, it goes negative after 3 time periods. A negative exponential never goes negative. If you're trying to model something which is always positive and your model goes negative, your solutions are going to be absurd. So perturbation theory was designed to, instead of trying to model, follow and find the solution as a polynomial in time, we'll let it be given by non-polynomial time functions, but expand it as a series in the parameter, measuring the size of the perturbation. And this is the way it carries out is very much like power series solutions. You express the solution as a trial solution looking like this, and now you just plug this into the differential equation, and the terms naturally gather in terms of powers of epsilon. This is the epsilon to the 0 term, this is the epsilon to the first term, and when you just take these 2 approximations, you get a very good fit to the exponential function. This technique was used in celestial mechanics by Poincare and Linstedt and their predecessors. But if you apply it to the spring, and here we're only going to forget about the nonlinearity. We're only going to treat the friction in the spring and use that as a perturbation. Your 0th order term is the classical undamped sinusoid, but the first order term correction looks like this. We'll look at the details in a second. And here's what the spring actually looks like. You see this decaying exponential getting smaller and smaller and smaller. But the solution, although initially it follows pretty close, it begins to deviate, and now the solution grows exponentially. You've got friction in the system, there's no way it's going to grow. And the reason that happens is because of the mathematical model you chose. The 0th order solution is fine, but the 1st order solution has this term what you call the secular term. It's there because the first order equation is driven by a resonant term, and a resonant term, if you remember your solution forms, resonant terms force you to introduce polynomials, multiples of the frequency, and these non-physical things, while they work for short times, they will eventually blow up on you. And speaking of time, I'm going to rush to the end here. My paper is sort of a tutorial paper, and it studies this for various examples. Excuse me, running through here. And the strain time solution that, or the Linstedt'S solution, says define a different parameter rather than real time, and try to choose that new parameter in such a way that these resonant terms don't happen. But it's very hard to motivate. And with multiple time scale solution, looks at, here you see the various terms in the damped oscillator for the exact solution. And you see there the 0th order solution is fast. There's decaying exponential, which is slow. And then there's this fine correction, which is so slow you don't even see the variation on it on this graph. And so this is called multiple time solutions. That is, separate the solution into rapidly varying terms, moderate varying terms, and slowly varying terms by looking at the exponential, by looking at the coefficient of time. This is a 1 times t and epsilon t and epsilon squared t. And now, in the interest of time myself, I'm going to jump here to the end. These are the mathematical details are not difficult. They're just like the normal technique of power series expansions, but you must choose the right form. And this is just a very quick solution to the damp spring problem. It looks like the exact and the approximation are pretty good, but not that good. But here, this is 1,000 seconds later, and they've only drifted this far apart. And how big is this? Is 10 to the minus 8. So these are the 4 types of procedures. The multiple time ansatz written in terms of separating time into fast, slow, and intermediate components. That's all I have time for, but I wanted to get the paper into the literature.
Thank you so much.